Welcome to this video on complex numbers and the quadratic formula. In this video, we're going to be talking about what complex numbers are and how they apply to certain situations that could arise when using the quadratic formula to solve an equation. To start off with, we'll do a little review of solving equations with 3 recognizable problems from earlier chapters and then 1 for a quadratic formula from a recent lesson. So please take a second to pause the video and solve for x in each of these 4 equations. In all 4 of these, we'll start at the top left and work through them one by one. The first equation is only a one-step equation. Easy to see that the answer would be -7 since that plus 8 equals 1. Next, we have 3x plus 1 minus 1 equals 0. You'd have to do 2 steps by adding 1 and dividing by 3 to get the answer of 1/3. Third, we have x squared equal to 2. In order to solve for x, we need to take the square root of both of these sides of the equation. And remembering that when we take a square root of x squared, we're going to get 2 possible answers that are coming from this equation. Keeping in mind that when you are squaring the square root of 2, that gives you a 2, so that works. And then if you do the same thing and square a negative square root of 2, well, that will be a negative times a negative and become positive. And then the square root would also disappear because of it being squared, just like the first answer choice. So both of these 2 answers would work. You could also write this as x is equal to plus or minus the square root of 2, like you might remember from quadratic formula. And lastly, I have demonstrated a quadratic formula to solve this particular quadratic equation. And you can see that the first step is putting everything into the quadratic formula and then simplifying the square root part to be just a 1. And then you're doing the positive version, which would be -5 plus 1 divided by 2 to get you -2. And then the negative version of -5 minus 1 divided by 2, and that would equal -3. All of these 4 problems we can solve and get answers for fairly easily based on our prior knowledge. So if we advance to our next slide, we've seen this number system image in prior classes before. We have the smallest group of the natural numbers, like 1, 2, and 3, and then whole numbers starting at 0, and then integers where we have all of the numbers like you see here, -1, -2, -3, and then 0, 1, 2, and 3, and all those numbers. And then you have rational numbers where anything that can be written as a fraction. So that includes fractions, repeating decimals, standard fractions, improper fractions, terminating decimals, all of that stuff together. And then you have a final group of irrational numbers where you have symbols like pi and then radicals like square root of 2 that give you an answer that would be a decimal, but the decimal itself does not end, and it also does not have any recognizable pattern. So we have all of these 5 different number groups based on all the numbers that people use in the everyday world. If we look back at our last slide at our answers, we needed specific numbers from those groups to say what those numbers would be. So -7, well, we know that is an integer, so we could use that as from that group of integers. 1/3 would be a rational number, so we use the rational number group. Square root of 2, negative square root of 2, those are both irrational numbers. And then we have -3 and -2. Those are both integers again as well. And you could think about, well, if we could get any of these equations, could have given us a 2 as an answer, so that'd be a natural number. You can always get 0 as an answer for an equation. And that means we're going to need whole numbers as well. And all of this should be familiar because we basically had mathematicians inventing these, are discovering and establishing these number groups to answer equations like you see in front of you. Now, we're going to continue looking at quadratic equations more here and think about what we've been working on lately in class. So you're going to be finding the discriminant and the number of real solutions for the quadratic equation you see in front of us, and then graph the equation and look for the amount of times it intersects the x-axis. And we want those answers to kind of agree with each other, because the number of real solutions for a quadratic equation usually is going to be the number of x-intercepts as well. So please pause the video here to see if you can find the discriminant, number of real answers, and set up a graph of this equation on a calculator or on desmos.com/graphing. The result of that process we have in front of us now. We have our equation in the top left corner. If we use our discriminant, b squared minus 4ac, we end up with a -4 as an answer. Whenever your discriminant is lower than 0, that means there are no real roots or solutions. Roots and solutions are really the same thing. And you can see in the graph, we have a parabola that never crosses the x-axis, so there really isn't any real solutions. And so you had mathematicians accepting this idea that there's just no way to find an answer here that makes any sense. So we need to think a little deeper to say we can't just leave it at, oh, well, there's no real answers. There's no defined integer or rational or irrational answer we could use here. But that doesn't mean the answer doesn't exist at all. So in this equation here, it's a very easy quadratic equation to solve. So I want you guys to use square roots and algebra to solve for an answer for x here and see what you get. And then whatever answer you get, try putting that into a calculator, see if it, and see what it ends up equaling decimal-wise as well. The steps for actually finding an answer here are pretty straightforward. It's only 2 steps: subtracting 1 from both sides, and then taking the square root of both sides. Remembering whenever you do that, you end up with a positive and a negative result for x as an answer. And we see that we have positive and negative square root of -1. Now, if I were to put square root of -1 into my calculator, it would give me an error message that says non-real answer. And that is very peculiar, as you might guess. And we need to think about how that kind of coincides with what we know about what the definition of real numbers are. If our calculator is telling us that this result here is not a real number. The 2 bullet points you could say are for the definition of a real number. You could say, well, any number that can be written as a decimal. So that's fractions, integers, everything could either be 0.0 or the actual decimal result you would get. The second definition is going back to elementary school when you first learned about counting and numbers, and all that goes into that is you use a number line. So any number that's a real number either needs to be on the left or the right-hand side of 0 on your everyday number line you remember from elementary school. Now, this square root of -1 doesn't belong anywhere on that number line. So it would need to be on its own number line. And you can kind of think of that number line being perpendicular to the one you saw in elementary school. So those people in class will watch this video. I will post a link for this video as well, and you can check that out for yourselves. It kind of goes into an explanation of that x squared plus 1 equals 0 equation and what we just talked about. So the idea of what we just looked at, the square root of -1, is what's known as an imaginary number, which is kind of a misnomer based on historical mathematicians who were part of the discovery of it. It's more of just a number on an alternative timeline. And like I mentioned earlier, we made all these real number groups for the different answers we got, and now we just have another type of number that we need a new type of number group for. And we'll call it imaginary numbers. There's a lack of other accepted description of it, but just know that it's not really imaginary. It's just new and different from the regular real number system that we already had. So whenever you see square root of -1, we're going to replace that with an I. And then you have I squared would be equal to -1, which is sort of an interesting result in that you're taking an quote-unquote imaginary number and squaring it. And if you square a square root, that cancels them both out, leaving you with just a -1, which is an integer and for sure a real number. And these imaginary numbers you can count like any other. You could say that you have I or 2I or 3I or 4I going up forever. There are lots of arithmetic and graphing you can do with imaginary numbers, but that is for a much later math class, and we're not going to be covering that for math 2 right now. Now, we've already had practice with square roots, and you can find those in prior videos where we had to simplify them. So I want to go through 3 of these examples and have you try some more of them on your own. So we'll start with the square root of -25. So if we know that the square root of -25, we could write that as the square root of 25 times -1. And that would basically be the same thing as the square root of 25 times the square root of -1. And that would end up giving us 5, which is the square root of 25, and the square root of -1 we're going to get rid of and write an I. And usually you want the I, you'll see a lot, it's kind of an italicized I, and it kind of hooks down to the right, the opposite of what a J would do. And that's kind of distinguishing it as definitely an I, basically in this case. So along this a similar line of logic, we can look at the square root of -3, and we could write that basically as being equal to the square root of 3 times -1. And then we can split that into 2 different square roots, one being 3, one being -1. And then you end up with basically the square root of 3 times I. Important to note that you make sure you're careful when looking at a problem and seeing what the square root is over and what it's not over. This isn't the square root of 3 times I. It's the square root of 3 by itself times I afterwards. And then lastly, we have the square root of -20, where we could kind of think about what we just did with the square root of -3 and basically make it into the square root of 20 being multiplied by I. But we can't stop there. We have to simplify the square root of 20 like we've done with square roots in the past. So we could do our tree method here. So 5 and 4 would make 20. And then 2 times 2 would make 4. And we could then circle, well, we got a pair of 2's, but only 1, 5. That means that our full simplified answer here ends up as 2 root 5 being equal times I being equal to what we started with of the square root of -20. So now using these examples, I'd like you guys to try the next 4 on your own and see what you would get as a simplified answer with I involved, and we'll have imaginary number answers. So you can see, looking through the bottom part, square root of -36 would end up as 6I. The square root of -10 would end up as root 10 times I. And the square root of -48, you'd split into square root of 48 times I. And then simplifying the square root of 48, you would end up with 4 root 3. So I'll just write that over here to the side. Using the same tree method, you'd be able to do square root of 48 equal to 4 root 3. And then because that -1 on the inside, you would end up with an I, and kind of this whole part right here would be your answer. Lastly, we have our problem at the bottom, 3 times the square root of -24. So you can simplify the negative inside to be the I part right here, right there. And then the square root of 24 would become 2 root 6 using the same tree method from earlier. And then the 3 at the front wouldn't have changed. And then last, you just have to do 3 times 2 and you end up with 6 times the square root of 6, and then an I on the end outside of that root. And that basically covers what you will have to do with simplifying negative numbers underneath of a radical. So lastly, we're kind of going back to using quadratic formula on the equation from earlier. So your first step, as always, would be putting all of your A, B, and C into your quadratic formula, simplifying it first, and then we end up with a negative 12 under our square root, which before we'd stop, but now we're going to keep going and simplify. So we'd separate the square root of 12 and the square root of negative 1, and then simplify the root. So we would have the square root of 12 would become 2 root 3, and then square root of negative 1 would become I. And then you can see now that we've done that, that the 2 right here and this 2, since we can basically divide all those 2's out, and we end up with it being equal by this our arrow here, that negative 1 plus or minus root 3 I would be, without all the 2's in it, over 1, or our final answer of negative 1 plus or minus square root of 3 times I. And this is kind of our next development here, in that we don't have just I in our imaginary number. We have a negative 1 in the front of it as well. So when we have a real number and an imaginary unit here together in one kind of big number that I've circled in orange, you have what's known as a complex number. So you can see here with our notes on complex numbers, you basically A plus BI, where A and B are real numbers, and then you have the I with the B making it the imaginary unit part, or the imaginary part, as you can see at the bottom left, and the real part kind of separate from it. And you have the whole complex number system where you have kind of real numbers and imaginary numbers coming together to make complex numbers together. In the next part of this video, we will be looking at solving these 5 problems as practice for the quadratic formula and getting complex answers as a result of them.